In the last video, we defined acceleration, and now we are going to explore the special case of uniform acceleration, or saying that the acceleration is equal to a constant. This is not always the case, so this is a special case. However, it turns out to be an incredibly useful special case, and many systems can either be reduced to this kind of a situation, or they can be reasonably well approximated as this kind of a situation. And trust me, you really want to avoid possibilities of things like acceleration changing. By the way, there is a name for that. The time rate of change of the acceleration is, I kid you not, named the jerk. And then if it gets even more pathological, the time rate of change of the jerk is the snap, the time rate of change of the snap is the crackle, and the time rate of change of the crackle is the pop, and I'm not making those up. As you can see, given the relative recency of those last three names, these don't come up very much. In fact, they almost exclusively come up if you're worried about doing things like launching satellites into outer space. So we will constrain ourselves to only looking at the cases where the acceleration is a constant. But this is something to be careful about, because sometimes you can get situations where, say, you drop a ball or something like that. When the ball hits the ground, actually the acceleration wasn't a constant because the ball was moving and then it came to a stop. If you think about it for a moment, when the ball was falling down, the acceleration point down, when it hits the ground had to somehow make it accelerate upward very rapidly in order to make it come to a stop. So it's not completely, we're not completely without peril here. So we do have to be a little careful and make sure that when we analyze our situations that the acceleration really does stay a constant. So we'll go ahead and say that the acceleration is a constant. So if that's the case, we can go ahead and plot a typical velocity time graph for the case where the acceleration is a constant. That would look, say, something like that. Okay. So since we've said that the acceleration is a constant, this means that all points here, the slope will never change. So we can just write the acceleration as being delta v over delta t. And I'm not going to bother drawing the vector signs because I'm just working in one dimension at the moment. So we're just saying the slope of the velocity time graph is a constant. Okay, well, we can follow that through. And one of the things we get almost immediately is you can say, well, delta v then would be equal to a delta t. Remember that delta v would be v final minus v initial. So we get that v final equals v initial plus a delta t. I'll go ahead and put a box around that and label that the first of our four of what I like to call the gang of four. Okay, so now let's go and take a look at this curve a little more. So let's say that we have an elapsed time here of delta t. So we'll say this time that elapsed here is delta t. We start at some speed v and some velocity v initial. We end at some velocity v final. Okay, so we know how to find the displacement. We know the displacement will be the area under the curve of this velocity time graph. And so we sit back and we really scratch our head and we remember from geometry here that the area of a trapezoid is the base times the average height. So delta x will equal the area under the curve. So this will equal, the base is delta t, and the average height would be 1/2 v initial plus v final. Okay, and delta x is x final minus x initial. So if I rearrange that all, I get that x initial is equal to, x final is equal to x initial plus 1/2 v initial plus v final delta t. And I will cryptically say that we just found the third of my gang of 4 kinematics relations. Now, if this is making you feel a little queasy inside, keep in mind that another way that we could think about this is that since the velocity is changing uniformly, the average velocity would have to be exactly in the middle. And so basically this missing area here is exactly equal to that extra area there. And so the area of the trapezoid is also the area of that box. And there we can say, yeah, average velocity times the time. I feel kind of good about that. So if that makes you feel any better, that's another way that you can think about it. All right. To catch the other 2 of the gang of 4, we're just going to be doing some algebra. So to get the first of these, what I'm going to do is I am going to take my solution for v final from equation number 1, and I'm going to stick that in to equation number 3. That will get rid of the v final, and let's see what that gives me. So that's going to give me x final equals x initial plus 1/2 v initial plus v initial a delta t times delta t. V initial plus a delta t. There we go. All right, so this is x initial plus 1/2 times 2v initial plus a delta t. Let's just start expanding things out here. So I've got that this is x initial. Now here, with this term, I have a 2v initial. I'll be timesing this by 1/2. So that's going to leave me just a v initial that I'm also timesing by delta t. And then here I have a 1/2 and an a, and then a delta t. And then I have to times it by another delta t, so I get 1/2 a delta t squared. This is the second of my gang of 4. And then to get the last of them, what I will do is I will take my first equation, I will solve for delta t here, and I will insert for delta t there and see what we get. So we're starting with v final equals v initial plus a delta t. So a delta t is v final minus v initial. So delta t is v final minus v initial over a. All right. And then we're going to stick that into here. So that's going to give me x final equals x initial plus 1/2 v initial plus v final times v final minus v initial over a. All right, first thing I'm going to do is I'm going to commute these two terms. And now, if you look at this, this should be really familiar. If we just do it off to this, if we multiply these two off to the side, doing the whole FOIL thing, right? First is going to be v final squared. Then outer is v final minus v final v initial. Inner is plus v initial v final, which is the same thing, so those cancel. And then last is minus v initial squared. So we are left with this being x initial plus 1/2 v final squared minus v initial squared. All right. And now from here on out, we're just manipulating things around. So 1/2 v final squared minus v initial squared. I'm just moving to the other side. This will equal x final minus x initial, which if you prefer, you could write as delta x. Then we'll times through by 2. We have v final squared minus v initial squared equals 2 x final minus x initial. Or finally, we end up with v final squared equals v initial squared plus 2. Whoops, I dropped an a right there. My apologies. There. Plus 2a delta x, or x final minus x initial, whichever you prefer. And this is the fourth of our gang of 4. All right. Let me recap this real quick and see what we're left with. So I'm going to make a little table, and I'm going to leave room to note what's missing. So we'll have our relation. Then over here, I'm going to put in parentheses what's missing, and notice I've got that in quotation marks. So the first of our gang of 4 is v final, v final equals v initial plus a delta t. And what are we missing? X does not show up of our 4 key kinematics variables. The next one we have x final equals x initial plus v initial delta t plus 1/2 a delta t squared. V final is nowhere to be seen. Likewise, x final equals x initial plus 1/2 v initial plus v final delta t. A is nowhere to be seen. And then finally, v final squared equals v initial squared plus 2a x final minus x initial. Delta t is nowhere to be seen. This turns out to be a really handy-dandy way of figuring out which of the 4 key kinematics relations we want to use in a particular situation. So before we get rolling with that, I'm sure you've seen in many places different approaches to tackling sciencey problems. So let me give you mine. Somewhere along the line, I stumbled across the acronym STAR, which stands for Situation, Tools, Answer, Review. So as we go along, we'll fill in more and more of these. But, just for a starter here, situation. You need to understand what is the situation and what is the question actually asking. Read it carefully and thoroughly. And then, before you go anywhere with it, draw a picture. And trust me, you've already seen how bad my artwork is. You do not have to be a good artist, but pretty much any physicist will tell you that by drawing a picture, it does an awful lot to help you visualize what's going on with the problem. In fact, even in higher physics, we develop diagrams just to help us continue to visualize things, even in situations where it starts looking really weird. Tools. Tools is going to be something that is going to be a key relationship. So here, I've got the gang of four, our relationships for constant acceleration. The other examples of what would be good tools to use, things that have pretentious sounding names are named after people or both. Newton's second law of motion, as an example, the impulse momentum theorem. As we go on in the course, we'll run into both of these. These are the second law of thermodynamics. Generally speaking, if the physical community has thought enough about it to give it some pretentious sounding name, then it's an important starting point. And I can't stress this enough. The issue here is that you need to start with things that are always true, apply them to the situation that you've got, so that you end up with a result that is true. So what would not be a valid relationship would be picking out some arbitrary equation out of some random page of your text that looks like it might happen to have the right letters in it. While that may indeed be a relationship between the quantities you care about, it might not be a relationship for the situation in question. So here's where physics differs from the other sciences. Our field has been around a lot longer. And because it's been around a lot longer, there are many more physical systems that we can look at. In a field like biology, it's a very exciting time right now for that field. It's just beginning to get really good into its quantitative revolution. But what that means is that in the earlier stages of a quantitative revolution, you tend to just have specific equations for specific systems, and that's the beginning and the end of it. In physics, we've been at the our quantitative revolution was about 350 years ago. And so we've gotten to the point where if we were to still be trying to keep track of individual equations for individual systems, there would just be way too many to keep track of. I tried to figure it out once and estimated that you'd have to memorize upwards of 10 billion equations. And since my memory at least isn't that good, what we've found in the physics community is that a lot of these things can be abstracted to more general principles that are always true and then applied to the situation at hand. So when I say tools as a good starting point, the equations at the end in the chapter reviews of a textbook are a good starting point. Like I say, it should probably be named after somebody or have a pompous sounding name or both. Okay, so that much there. Physicists often call the combination of these two setting up the problem, and there's a lot of solid physics work that you have to do. Then in the answer stage, you've identified the tools that you're going to be applying, the relations in question. You're going to solve them for the thing that you need. So here now you're just doing a bunch of math. And I have two things to say. First thing is letters good, numbers bad. And what I mean by that is don't stick numbers in right away. The only number you should ever seriously contemplate sticking in right away is 0. Anything else tends to lead you into a world of trouble. From the practical issue is that if you stick all of your numbers in right away, you're still going to be doing a bunch of algebra. But what winds up happening is that if you mess up the algebra, usually there's no way to track it down, and then you have to start all over again, and you just wasted a ton of time. Also, there's the issue of accumulated round-off error. I have seen it be the case when students have presented work to me that they've had and that they did everything technically correctly, but because at each step they took their result, they wrote down just a few digits of it, they stuck just those few digits into the calculator and then did the next step and so forth and so forth. You would think this would be no big deal. You would think that the rounding would just cancel itself out. It doesn't. Mathematicians have shown that typically what will happen is once you start rounding in some direction, it just keeps snowballing. And I've had students come in with answers that were 20% off due purely to accumulated round-off error. Now, sometimes maybe just being 20% off is fine. You just want to know roughly what the value is. But, other times it matters a lot. I'm given to understand that there are classes of chemotherapy drugs where you give the patient 1% too little and you don't really do anything for their cancer, and give them 1% too much and they're in a world of hurt because some chemotherapy drugs are themselves poisons. And so it can have really bad other outcomes for the patient. So to avoid things like accumulated round-off error, if you stick with it all as letters to the bitter end, and then stick in your numbers, and when you stick in the numbers, make sure you stick in the units too. You resolve all of those issues by only having your calculator grind through the numbers once. So then we get back to the review side of things, and this is more physics. So here, do the units check. If you're expecting an answer in meters and you get seconds cubed per meters to the 5, odds are that you made some sort of a math mistake. Now, if you're expecting meters and you get meters, that doesn't mean you didn't make a mistake. But if you're expecting meters and you don't get meters, that means you definitely did make a mistake, and you should go back and check where you went awry. The other thing you should ask yourself is the answer reasonable? When you're doing physics problems, please don't check your common sense in at the door. If you're solving for the final speed of a baseball, you might be aware that it's really something for a pitcher to throw a 100-mile-an-hour fastball. If you wind up getting the speed of the baseball to be going at, say, 50% of the speed of light, you might suspect that you probably made a math error somewhere, and you should go back and check the math. So the first two phases are some physics, and you have to dink around in the land of math for a while to get the number you want. And then at the end, you do some physics to check that it all makes sense. So with this, let me work through a couple of sample problems so that we get some feel for how this might work. So I'm going to go ahead and take a look at a car. And again, yes, I know that my cars all look like mid-80s Volvos. Just deal with it. So here we go. We got my car. And we know that we traveled 100 meters. So notice here what I did was I set x initial to 0. You're generally free to do that. If the problem says something like a car traveled 100 meters, you can make x initial 0 and x final 100. And how long did we do that for? We traveled 100 meters over 5 seconds. So here I drew a little clock with delta t equals 5 seconds. So this will allow me to say that t initial is 0 seconds and t final is 5 seconds because no times of day are being specified in the problem, so I'm free to do that. I'm told at the end of 5 seconds, the car is now traveling at 30 meters per second. So I would like to know how fast was it going initially. Okay, so that's my situation. I drew a picture. I identified everything I knew. I identified what I didn't know, and I identified what I was being asked to find. Now, for identifying tools, if you suspect that kinematics would be the way to go, and here you've got no reason to assume that the car isn't accelerating uniformly, you can then go and look for what is missing here. So the missing variable is one that is neither asked for nor given. So in this case, the acceleration is what is missing. I can then go to my 4 key kinematics relations and use what is missing to identify what I need. So I go back here and I say, oh, hey, A is missing. This is the starting point I want to use. So let's go ahead and write that down. Oops, let me keep that on the screen there. Okay, so x final equals x initial plus 1/2 v initial plus v final delta t. Now, what we're being asked to find here is this v initial, but we know everything. We know literally everything else. We know x final, we know x initial, we know v final, we know delta t. So we're good to go. Now, here again, I would say do everything in your power to restrain yourself from sticking in any numbers that aren't 0. So you're okay with saying that x initial is 0. You can go ahead and put that one in right away. But even though you have all the other numbers, hold off on that, because if you stick the numbers in, the math is going to be a mess. It'll be a lot easier to make mistakes than if you keep it all as letters. So this is a habit that you really want to practice and get used to. So we're trying to find v initial. So remember, the key game in algebra is to unwrap the present, right? V initial is the present. We need to do inverse operations to unwrap the present. So first I'll just put everything to the other side. So we're not doing physics at this point. At this point, we're just having to do some algebra to get what we want. All right. So I realize if I multiply both sides through by 2, I'm closer to unwrapping the present. V final, sorry. Heck, stop it. V final. So, okay. And I'm still being times by delta t here. So if I divide both sides through by delta t, right? Now I'm even closer to what I want. And then finally, I want v initial. So if I subtract v final from both sides, I have what I want. V initial equals 2x final over delta t minus, I'm sorry, we're looking for v initial, my bad. And see, that's part of the advantage of this, is that If you catch a mistake, it's easier to fix. So v initial is equal to 2x final over delta t minus v final. Okay, now you can go ahead and stick your numbers in. So what do we have? We have 2, great, 100 meters over 5 seconds minus 30 meters per second. Okay, now before we go anywhere, do the units check. Well, here I have meters over seconds. If I add or subtract two numbers, they have to have compatible units. So meters per second, that's good. The result will be in meters per second, which is what I'm expecting because I'm solving for a velocity. So this is going to be what? 200 over 5 is 40 minus 30 is 10 meters per second. Is that reasonable? Yeah, the car was speeding up, it started slower. The number's in the same ballpark as V final. We're not expecting cars to have crazy performance or anything like that. So yeah, that seems like a very reasonable value. All right, let's go ahead and do one more example, and then I will go on a small rant about free fall. So in this problem here, what I am imagining is that a car is initially going at 100 meters per second. It slams on the brakes, and after it's skidded 100 meters, it's now going 40 meters per second, and I want to know the acceleration. So again, I can make x initial 0. I can make x final here 100 meters. I can say that v initial is 100 meters per second. V final is 40 meters per second. And we want to know the acceleration. All right, now can we use our horse sense about this to say anything? Sure. The arrow is getting shorter. So that means that the since we're slowing down, we already know that the acceleration has to be pointing to the left. So that already tells me that the answer is negative. So when I get to the review part of the process, if I don't get a negative answer for the acceleration, then I know that I'm in trouble. All right, so I've identified everything I know. I've identified what I'm being asked to find. Now it's time to identify the tools. We know the acceleration is constant, so we can use the gang of 4 kinematics. So we want to identify what's the missing variable, the one neither asked for nor given. I neither asked for nor gave the time. All right. So that means that I can use v final squared equals v initial squared plus 2a x final minus x initial. And again, the only number you should ever put in right away is 0. All right. What are we being asked to find? We are being asked to find the acceleration. So again, we go through the same process of unwrapping the present. So now we're just doing some math for a while. We're not really doing any physics at this exact instant. So let's get this term all by itself. To do that, I will subtract v initial squared from both sides. So 2a, and I can just say x final equals v final squared minus v initial squared. And then to get a, I need to divide by 2 and x final. All right, so a equals v final squared minus v initial squared over 2 x final. All right, let's put in our numbers and see what we get. So this will be 40 meters per second squared minus 100 meters per second squared over 2 times 100 meters. Oh boy. So when we're doing this here, we really should be, sorry, I forgot to put in the A and the R here. A. R. Okay, so now here we really got to work at this to make sure that our units make sense. We know they should be meters per second squared. Let's see, are they? All right, first off, we do know that here I have meters per second that I'm going to square. That's going to give me meters squared over seconds squared. Same thing's happening with the other term. So the numerator will be meters squared over seconds squared. I will be dividing by meters. Cancel, cancel. I'm left with meters per second squared, which is indeed the units that I would expect for acceleration. And so I get negative 42 meters per second squared. Well, is this reasonable? Yeah, it's a little over 4 Gs. Well, that's awful hard deceleration, but we're talking 40 meters per second and 100 meters. We're pretty clearly talking about something like a Formula One racing car or something like that. So yeah, in the context of a Formula One racing car, that makes some sense. Plus, 42 is the answer to the ultimate question of life, the universe, and everything. And yes, your instructor is that big of a nerd. All right, one quick rant. Books tend to fall into a trap when they talk about free fall. Now, in free fall, this is vertical motion. And in free fall, the only force is gravity. If that's the case, the acceleration is equal to negative 9.8 meters per second squared, with the negative sign meaning down. A lot of books will then blithely put in negative G, but I very strongly urge you to get out of that habit. To be very fussy about it, in this case it matters. Books will often, because they haven't gotten there yet, they'll say this is the acceleration due to gravity, and that's not correct. If the it's actually a quantity called the gravitational field strength, and the correct units for it should actually be written as newtons per kilogram, which have the same physical dimension. More on that later as I get into a big, huge rant. But if you are doing problems where the only force is gravity, so something could be going up and slowing down, as long as the only force acting on it is gravity, and usually what you're told to do is to neglect air resistance because it's really way too hard to take it into account, then you can go ahead and just write A equals negative 9.8 meters per second squared in a case like that, if the only force is gravity. Now, if we're looking at, say, a skydiver or something like that, you'll have gravity pulling down, but then there's going to be drag on the parachute pulling the skydiver up. In a case like that, the acceleration is not negative 9.8 meters per second squared. We don't know what it is without doing more work, but it's pretty much guaranteed to not be that. Not only that, but that 9.8 number only works if you're near the surface of the Earth. General rule of thumb, if you or a machine can breathe air, so basically as high as the highest jet aircraft can fly, that acceleration works out to be 8.9 meters per second squared. But by the time you get to, say, the altitude of the International Space Station, an object that is freely falling to the center of the Earth, at that altitude, it's only 8.9 meters per second squared. And this is just because the force of gravity is a little weaker out there. get out to where there are telecommunication satellites, and that number is a little over 0.2 meters per second squared, and so forth. So my big caution for now is that when you see a free fall situation, just immediately write that A is negative 9.8 meters per second squared and get on with your life. There's no need to have any additional equations that have G's in them. They only serve to cause more problems than they solve. So anyway, with that, in the next series of videos, we'll start looking at kinematics in 2 dimensions. Have a good one.